Hello, everybody. Today I'm going to present uh, my talk on optothermal pulling and trapping of colloids using nanowire plasmons. This work was done in collaboration with my students Vandana, Sunny, and Deepta. And I'm going to first give you an overview of the topic of what is interesting about light-driven active matter and the motivation for that. As all of us are aware of the fact that driving systems out of equilibrium has created very interesting paradigm in terms of active matter, and light actually can be a very powerful tool to push the system out of equilibrium, especially when the system happens to be soft matter in nature. So this process of light activated process of light activated matter happens to create some very interesting opportunities to study systems out of equilibrium. And given that you can control and manipulate light with extremely high degree of accuracy, it creates some very interesting opportunities. There are two questions which are fundamentally of interest to us. The first is how do optical and optothermal forces drive soft matter? So the kind of soft matter which we are interested in is colloids, liquid crystals, droplets, bubbles, etc. There can be also specific questions related to what can we learn about structure and dynamics of soft matter, especially those structures which are driven by optical and optothermal forces. Now, this has encompassed as a very nice subset of questions related to driven active matter, and there are some very interesting prospects as I'm going to kind of discuss it furthermore. Now, the kind of methods that we use are mainly the optical and optothermal tweezers, where we utilize the technique of trapping and manipulating colloids at reasonably high accuracy. And also we ask the question of how does these colloids actually kind of trap, move around in the presence of plasmonic fields, and this is something which is of interest to our research. Now, before we go into the specifics of this particular interaction, let me give you a very brief tour of surface electromagnetic waves. So, surface plasmon polaritons is essentially the coupled oscillation of light and the charge density oscillation. So, if you take let's say a metal like gold, and if you illuminate that particular metal at a particular angle using a specific defect which is present on the metal, say, then you end up exciting a coupled electromagnetic wave where the electric field decays exponentially on either side of this interface. So if you have a dielectric medium on the other side of the metal, and if that contains a fluid in which you will have colloids, then the colloids actually can undergo some very interesting motion in such kind of external electric fields. And this can also facilitate some kind of potential wells where you can trap and manipulate colloids in this particular situation. So another important aspect is that when you illuminate a plasmonic nanostructure, they also generate heat. This is a very important consequence because if you now consider the electromagnetic radiation, and you have an external electric field facilitated by that illumination, the electric field now couples to the metal such that the imaginary part of the dielectric constant actually couples to the electric field, and this coupling leads to a generation of heat, and where you can quantify the power density of this particular heat, which is given by this particular formula, where omega is the frequency at which the light is being illuminated. Now, the consequence of this kind of illumination is that you now have, for a given volume of a nanostructure, you end up actually having a total power absorbed, which is now given by this heat power density times the integral over the volume. And interestingly, this total power absorbed by that particular structure can be connected to the absorption cross section times the intensity of the light what you are illuminating. So the important message in this slide is that when you illuminate plasmonic nanostructure, you can generate heat. And what we are interested in is to utilize this optically illuminated plasmonic nanostructure to manipulate and also assemble soft matter systems. And that is the question we are trying to address here. So let me give you one of the recent examples from my lab. So one of the structures what we have been studying is, let's say, a kind of a two-dimensional metal strip, or in this particular case, a plate of gold triangle. In this particular micro triangle, if you now deposit this particular triangle, which is prepared, by the way, using chemical synthesis process, and you deposit this using a drop cast technique, and if you illuminate a light at a particular angle through total interreflection, if there is now colloids, in this particular case, if you have, let's say, silicon dioxide colloids, they show some very interesting assembly process and dynamics in such a situation. So shown here is the optical illumination schematic of such kind of an experiment. Let's see the consequence. Because of such kind of illumination, you end up getting some very interesting accumulation of colloids. In fact, in such a situation, because of the optothermal potential created by such kind of triangular structure, you end up assembling colloids in a two-dimensional assembly. They exhibit fascinating crystal kind of hexagonal symmetry, and you can study two-dimensional assembly in such kind of structures. Now, more pertinent to this particular talk is this concept of optothermal pulling and trapping using plasmonic nanowire, and this is a recent work which has just appeared in Soft Matter. The idea is that instead of having an extended structure which is either two-dimension or three-dimension, we use a quasi one-dimensional nanowire structure. The advantage of this kind of structure is that you end up exciting so-called propagating plasmon. The idea is that you illuminate one end of the wire. This kind of facilitates plasmon propagation along the length of the wire. And if there is a colloid in the vicinity, this particular colloid actually starts getting pulled to the point of excitation. We were interested in looking at the dynamics of this colloid as a function of space and time, and also the consequence of such kind of pulling when the colloid reaches the excitation point. So shown here is actually the plasmon propagating wire, where you can clearly see that when the electric field of a green laser, 532 nanometer excitation, is now focused on one end of the wire, this particular light gets converted into plasmon, and at the end of the wire, there is now the reconversion of plasmon to the photon, and there is now an optothermal potential created by such kind of excitation, which is what we tend to utilize to draw the colloids in this particular situation. And this is a scanning electron microscope of a typical nanowire, which is used for such kind of an experiment. Now let's look at the what happens. So the kind of technique what we use is essentially an optical trap, where you are using an optical trapping microscope and also looking at the particle dynamics. So what I'm going to show you to begin with is the optothermal pulling effect, where you can see that the excitation is now at this particular location, and we have filtered that light so that you can visualize the colloid with ease. So once you illuminate this wire, you can see that the colloid makes a very nice kind of motion, which is essentially a pulled colloid. Now the colloid, having now reached the excitation points, exhibits a very interesting the motion of trapping, and this colloid is static as long as this excitation is present. So I'm replaying this video once again, so you can see that the colloid gets kind of trapped in the location of interest, and this leads to some very interesting dynamic process. Okay, now going further, if you look at the mechanism of this whole principle, this can be now studied in significant detail by looking at the dynamics of the single colloid as a function of time. And if you now extract the trajectory of this particular colloid, there's a very nice linear motion of the colloid. And if you also further look at the mean square displacement as a function of the lag time, you can easily fit that particular curve to kind of two different power laws. One happens to be such that it is essentially into the conventional Brownian dynamics, and it also changes its slope because of the increased in velocity as it comes to the vicinity of the wire. So the exponent actually changes from one particular location to another location, and this can be easily understood as Brownian dynamics in a under linear force kind of one-dimensional potential system. And importantly, once the colloid reaches this particular excitation point, they also get trapped. And this is actually kind of the trajectory they actually take at the end of the wire. So they hover around the wire and keep actually moving in this particular location where the wire axis, the end of the wire is indicated. And this is the particular location where the excitation is also present. So it shows a very interesting dynamics, which has some very interesting consequence of how the colloid interacts with the plasmonic nanostructure. Now, we further went and looked at the reason why this kind of trapping motion happens. One of the significant reasons is that there is a very nice temperature distribution due to the optical excitation. So this is a three-dimensional numerical simulation of optothermal excitation of the plasmonic wire. So at the location of interest, you see that there is now an excitation of laser light beam at 532 nanometer, and there is now a very nice gradient of temperature along this particular wire. The silica colloids happen to actually be thermophoretically interacting with this particular structure, and therefore they move from a lower temperature to the higher temperature, and thereby also indicating that there is some kind of thermophoretic interaction. Because if you now use a similar kind of situation and replace a silica colloid by a polystyrene colloid, which actually has a different, or it has the sign of the Sorey coefficient is opposite to the silica colloid. They do not exhibit such kind of pulling motion, and therefore this indicates that there is an optothermal effect which is associated with this kind of a situation. Importantly, you see that the excitation here is along the wire, and I'll show you in a few minutes that once you change the polarization to the perpendicular excitation, the dynamics changes a little bit, which is also an interesting handle to assemble these colloids. So until now, I am talking about single colloid dynamics. What happens if you increase the concentration of the colloids and look at the multiple particle assembly? So I'm playing a video of the situation where the colloid actually starts now forming a beautiful two-dimensional assembly around the wire. So you can see that as a function of time, the colloids pack along the length of the wire and also perpendicular to the wire. And this particular process actually is mainly driven by the optothermal potential, as I have been talking about, and also leads to kind of an emergence of two-dimensional crystal as a function of time. So, which you can study as shown in this particular view graph. You will also be able to look at this dynamics of the individual colloids, and you can see that as the colloids are away from the wire, their mean square displacement actually increases, thereby indicating that the optothermal potential decreases as you go away from that particular wire. And this is also the mean square displacement plotted for the collectively for all the colloids. And as a function of the time, you'll see that they essentially become static in nature, indicating a kind of an assembly which happens as a function of time. Now, interestingly, there is an excitation polarization dependence. So if you have your polarization along the length of the wire and perpendicular to the length of the wire, the assembly process changes. So you can see that as long as the wire is illuminated along the length in terms of its polarization, there is a very nice packing efficiency which is observed. Whereas if you incident light in the perpendicular direction, then the trapping happens only at a location of interest, and it does not show the kind of large-scale assembly which is expected when you illuminate the wire along the length. Now, furthermore, you actually can look at this in certain detail and ask why is this polarization dependence coming into picture. And one of the fundamental reason is that the temperature gradients drastically change, because this particular gradient changes when you illuminate the wire along the length and the perpendicular to the length of the wire. And this is one of the possible reasons why the assembly process along the length and perpendicular length changes the dynamics of the colloids, and this has some very interesting implications. So to conclude, what I have discussed about is the light-driven soft matter process, essentially kind of realized in optothermal trapping and tweezing approach. And we have been studying this kind of approach in various different systems in my lab, including nanoparticle systems down to the single nanoparticle level, where we can see that we can study the dynamics of single particle which has been trapped using so-called thermoplasmonic tweezers, which is something relatively new and it has some very interesting consequences to study dynamics down to the single nanoparticle. Now, this is what I discussed mainly today, and this is something which we have been also doing. And these two regimes are essentially at the dielectric colloids. You can also study such systems in nanoparticle systems. So there is a lot more to also explore, which is something interesting, and I'd be happy to discuss during the interaction session. Finally, let me acknowledge my group members. Vandana Sharma was the main person who did majority of this dielectric colloids experiment, ably assisted by Sunny and Deepta, who also played significant role in nanoparticle trapping. And the initiation of this work was through my former PhD student Partha, who played a very critical role, and also some MS students Rohit and Utkarsh also had a very important role to play. I also thank all the other group members for the support, and importantly funding agencies for their continued support. And thank you all for your kind attention. I'd be happy to take questions.